Have you ever wondered why salt vanishes when you stir it into water, while oil stubbornly floats on top? Or why sugar dissolves into an invisible sweetness, but sand simply settles to the bottom? Your kitchen is actually a chemistry lab full of clues. Today, we're solving one of those everyday mysteries. Everything you touch is made from two fundamental types of compounds, and learning how to tell them apart will change how you see ordinary things. Over the next few minutes, we'll zoom in on crystals and molecules, run some simple demonstrations right here, and reveal the invisible rules that dictate why materials behave the way they do. Stick around. This will make your next cup of tea look like a science experiment. This is table salt under extreme magnification. Look at those tidy, repeating geometric faces. Each crystal is a rigid lattice, a repeating arrangement of positive and negative ions stacked like a three-dimensional checkerboard. Salt is an ionic compound. When sodium and chlorine react, sodium donates an electron and becomes Na+, while chlorine accepts that electron and becomes Cl-. It's a transfer of charge, not a sharing. Think of it like one partner handing over a priceless coin and the other guarding it. That exchange creates strong electrical attractions that hold the lattice together. Chemists call this lattice energy. Now, watch what happens when water gets involved. Water molecules, polar and bendy, wedge themselves between ions. The slightly negative oxygen faces an Na+ ion. The slightly positive hydrogens face a Cl- ion, and each ion becomes surrounded by a protective hydration shell. Those shells overcome the lattice energy and pull the ions apart, one by one, freeing them to move independently through the solution. That freedom is why salt seems to disappear. The crystal is still there as ions, only now dispersed. Particle size, charge magnitude, and temperature all influence how readily an ionic solid dissolves, which is why some salts dissolve faster than others. Now look at sugar under the same magnification and you see something softer, less regimented. Sugar is a molecular compound. Its atoms form covalent bonds by sharing electrons, creating discrete molecules rather than an extended ionic lattice. Picture roommates splitting rent. Instead of one person handing the whole bill to another, the electrons are shared. A single sucrose molecule is a compact, three-dimensional structure with specific angles and functional groups that make it soluble but keep the molecule intact. When sugar dissolves, individual sugar molecules separate from the crystal and disperse through the water, but each stays whole. That's a key difference. Ionic salts break into charged particles. Molecular compounds usually stay as neutral molecules. Oil molecules are another kind of molecular compound. Long hydrocarbon chains where carbon and hydrogen share electrons to form nonpolar bonds. Nonpolar molecules lack regions of partial-partial, potential, and negative charge. So water, which is polar, has nothing to grab onto. That's why oil refuses to mix and instead forms droplets. These molecular traits explain why some flavors, medicines, or stains behave differently. Polarity and bonding determine whether something mixes, spreads, or remains stubbornly separate. Because ionic compounds break into charged ions and molecular compounds mostly remain neutral molecules, their behaviors diverge in everyday ways. Polar water dissolves polar and ionic substances. Nonpolar solvents dissolve nonpolar substances. Try this quick experiment. Add a teaspoon of salt to water and watch it vanish as ions separate. Now add oil. See the beads and slick surface? Different rules at work. Those free ions also conduct electricity, so ionic solutions carry current, while most molecular solutions do not. Ionic solids tend to have high melting points and are brittle because pulling ions out of the lattice requires huge energy. Molecular solids often have lower melting points and different mechanical properties because molecules are held together by weaker forces. This explains why salt melts ice. Dissolved ions lower freezing point. Why soap cleans grease. Soap molecules have both polar and nonpolar ends to bridge water and oil. Why metals conduct electricity. A sea of delocalized electrons. Why plastics are flexible, long molecular chains. and why diamonds are so hard. A network of strong covalent bonds. Understanding ionic versus molecular compounds gives you a toolkit for predicting material behavior, solubility, conductivity, melting point, and more. The next time you stir, season, or clean, remember, you're watching two different worlds of matter interact, each with its own superpowers. Now that you know the secret rules, you can spot them everywhere around you.